All right, so lesson 33 is applying counting principles. This is where we're trying to find out, we're learning the probability of a certain event or how many outcomes the event can have. So one of the things we need to know is what we basically do each time. We start this off by drawing a diagram. For instance, if you want to know what are the total number of outcomes of tossing a coin, we start off with, the first one would be heads or tails, but then after that, if we say 2 coins, okay, we branch that off and you could get heads, heads, or heads, tails. You could get tails, heads, or tails, tails. And we see it goes from 2 to 4. And if we continue to branch it off, we're going to see 8. So we see that when we do this, as we increase, the more times we flip the coins, in order to find the probability of an event or the number of occurrences, we multiply each time. And that's important to remember, is that with each separate event, we're going to multiply. So if I flip 3 coins, then you have 2 total outcomes in the first coin. You have 2 total outcomes when I flip the second coin, and you have 2 with the third. So it's important to remember, and this is the fundamental counting principle, is that when we're trying to find these total number of outcomes, and it could be anything from some problems you're going to ask different shirt colors or different marbles, we're going to multiply that. So 2 times 2 is 4 times 2 is 8. So if I flip 3 coins, and we could draw this by a diagram, but we don't have to do that. We can just simply remember this principle, especially when we get into larger. As it branches larger, we could do the math rather than write that out. That's going to save us some time. But the key thing is to remember, multiply each of these to get how many total outcomes we have. All right, we're going to do a few of these. You take a look at example number 3 from our textbook. It says, using the fundamental counting principle, is what we just talked about, remembering to multiply each event. It says, a student's choosing a 3-letter password to use for an email. How many passwords are possible if the letters may be repeated? So example number 3, we have a 3-letter password. So you can do this, you don't have to draw boxes, but if we draw this, we have 3 boxes to fill. The first one, we would have, how many possibilities do we have to choose from? Well, we have 26 letters, so we have 26. Now the next time the same letters can repeat themselves, we can use the same letter again. So each time is going to be 26. Now to figure out the total number of possibilities, we use this fundamental counting principle that says we just multiply each separate event by themselves. So we take 26 times 26 times 26, which gives us, there would be 17,576 possible outcomes we could use for our password. All right. Letter B says, how many passwords are possible if the letters cannot be repeated? So this one's a little bit different. So if it cannot be repeated, the first one we choose from, we have 26. But since we used one of those letters, we can't use it again. The number of outcomes that we have to choose for the second letter would be 25. And then to do the third letter, we have one less than that, which would be 24. And then we're going to still apply this fundamental counting principle that we're going to, when we're doing the total number of outcomes, we're going to multiply each one of those. And when we do that, we get 15,600. All right, we've got independent and dependent events. And when they're talking about independent and dependent events, an independent event means that it does not depend on what happened before it, okay? And then the independent one is going to, or the dependent one is going to depend on what happened previously. All right, so look at example number 4, and they have different types there. It says letters A through E are written on 5 index cards. A card is chosen at random, and then another card is chosen at random. Determine whether the events in each case are independent or dependent. So letter A says, choosing A, then choosing B, if the card is replaced before the second card is chosen. Okay, so letter A in example number 4. Okay, we choose A and then choose B. the first card is replaced before the second card is chosen. So what this means is that they're going to put the card back in. So since they put that card back in, this would be an independent event. Because if we put it back in, the letter B, it doesn't depend on what we selected with the first one. All right, letter B says choose A and then choose B if the first card is not replaced before the second card is chosen. Now this would be a dependent because the second event is going to depend on what I picked in the first event. So we label that as dependent. All right, example number 5. And now we're going to apply this to solve. All right, so there are 6 positions in volleyball. Left front, center front, right front, left back, and center back, and right back. How many ways can 6 players be placed in the 6 positions? All right, so we are selecting our players' positions. And we'll put 6 boxes because we're choosing 6 positions. So for the first one, we would have 6 positions to choose from. Now, once we've chosen a position, the next event, or the next position, we only have 5 to choose from. All right, and after we chose those, now we've chosen 2 positions, there would only be 4. Okay, so this would be a dependent event because it depends on what we chose previous. All right, we just go down the line. Okay, this would be equivalent to 6 factorial. We put that in our calculator. So we've got 6 times 5 times 4 times 3 times 2 times 1, applying that fundamental counting principle. And when we do that, we have 720 ways that we could put these players in the 6 different positions. Okay, that's it for lesson 33.